let's get started. I brought you 5 ideas. One of the ideas is a slide deck, which looks gorgeous. So look forward to that. It's going to be number 2. This is vaguely motivated by me reading stuff. I normally work in mechanism design, macroeconomic theory. Yeah, can we switch this off? It's like less distracting. Just switch off the TV. From there? Okay, perfect. I normally work in mechanism design or macroeconomic theory, and there I'm like much more of an economist than an algorithmic game theorist. And I recently also work in reinforcement learning, and they're actually coding realities. So some transition into more practice, but you can query the economist Pat, who's a classical social scientist, and you can also query the reinforcement learning head who is going then to talk more about practical coding realities or how you build systems. The first idea is just an overview of how you improve systems in the corporation sense that we have already seen. And one structure that I want to get into your head, which is the first idea, is that really 3 different approaches that you can go for. One, I would call the mediator base. You're having a couple of agents that interact in some way, and you're introducing a mediator into the system. There's a ton of work under the name of stackable games that work in this environment. You're essentially introducing a new agent that proposes, gives mediators. Let's just wait for a minute. Yeah, no, I prefer having. Wait, we're not in a rush. So we have introduction of new agents. This comes out, for example, when I read that the protocol becomes aware in the RAM that was in one of the texts, or the protocol tries to do something. There's an agentic nature to the protocol, and you're introducing a new agent. The second approach I would call the declared leader. This would be like of the sand, the sign. This is endowing particular agents with specific actions that constitute commitments. We have this in the real world a lot, where we have hierarchical structures that allow some agents to make commitments for others. And the paper that I'm going to present uses this style, and we can digest that. The third one is equilibria. So here, this one agent thinking of the threat, which is learning something of the form: I am going to not be too naughty here on this ship, because otherwise the police come and puts me into jail. Like, probably I would need to really break a lot of norms so that happens. But this threat is there, and I'm cooperating for that reason. This is what I would call subgame-perfection. So we have these 3 ones, and for me, as an outsider to crypto, kind of, like, I read a bit before this talk now, I would say that the first one, which has a bunch of work now in academic venues, but also with just stackable technology, doesn't sound very crypto as in some way, because actually it introduces a centralized agent that has, again, a lot of power. So here the question becomes, okay, there are 2 ways. One, learning punishments. I actually disagree with the statement that punishments are bad. Like, we have a lot of very good emergent behavior because we actually don't punish if the punishments are in place. People just don't choose to not do it. And there are other things that are essentially technology. And I will interchangeably also talk about agents versus the technology. Sorry, this technology should go here. Now let's go. So I'm happy as the second idea to give you an example of concrete reinforcement learning domains that we're working in. This is the main thing that I think for you is interesting here. It is motivating social dilemmas, which I think you as an audience don't need, but you will see what the game looks like as a simulator. I'm going to finally talk about two very concrete things that are apparent if you're training reinforcement learning systems that I haven't heard or read. The main question of cooperation, and also this paper, is how do you get selfishly motivated agents to cooperate? We already heard of a lot of them. There are many that are actually still quite far away. The autonomous vehicle things, we're probably 10 plus years away to see that. We have, however, things where control systems are already out there. Smart grids are control systems, and having smart meters and Google Nest have things that have agentic nature already right now. So this is quite close. This paper is very motivated by warehousing solutions where you have robot fleets that are in an Amazon warehouse doing packaging fully automatically. Here you have some very clear cooperative framing. Is Amazon controlling all of the robots, but the robots are independent for computational reasons. There are also other esoteric ones in manufacturing that I'm not going to go into. The domain that we are working in is the grid world domain, which features a river, a tree, and a robot. The robot gets rewarded by picking apples. When the robot goes and grabs apples, over time, there's a buildup. Oh, what is this? Yeah, I can't see my. It's weird. I cannot see the cursor, but now I can admit. There's dirt building up in the river, and the robot needs to go and take another action, which is cleaning pollution. Pollution cleaning does not yield reward. So they clean the reward, there's again an apple. So in a single agent setting, you have the cycle from polluted, the robot goes to clean, apples grow, the robot picks apples, it builds up pollution again, and it is in the cycle. This is something that a reinforcement learning agent can learn reasonably well. You need a couple 10,000 things. I'm just going through this bit in like 2 minutes. Whatever is it, we have more agents. You might hope that they go, they clean, they grow. At some point, they realize that they could divide labor, and one cleans, one eats apples. Pollution builds up, they both harvest. Does this happen? Yeah, not really. Because both agents, so what you see, both agents end up waiting for apples that don't grow because the river is there. Because the agent who would be in this model, the harvesting agent gets apples, the other one gets dirt, but the second agent doesn't really get anything. We have a social dilemma in this one, which has also an intertemporal component to it. So I think now is a good time. If you have a question?
I was just wondering if the pollution is in some way related or dependent on the apple picking out, or
just by time, just over time. The logic is if there's a certain dirt level, no apples grow, right. But pollution increases over time at a constant rate. Now, how do you train this thing in environment? I already said for a single agent, you can just view this game as a very big game. There's some state, there's some actions. There is this now pretty wide algorithm that's pretty widely used that's called proximal policy optimization, which optimizes whole policies, so whole functions from state to actions. And yeah, here I will report rewards as number of apples that are picked per an episode. You could do separate training and you will converge to some form of Nash equilibrium, where agents might randomly go out and clean and go out and pick apples, but this is some approximation to complicated looking mixed equilibrium, which is not very high performance. You can have one agent that controls all robots in this environment, and you see some performance. Interestingly, you can also look at benchmarks that I'm not going to talk about, and you can allow for a commitment. And you see here that this example, the commitment decentralized solution that we are proposing this paper outperforms even joint. Which looks for now surprising, but I will tell you why that is. So let's see what commitments can do. Here, I think it's clear the whole meeting here is about commitments. I will commitment share my apples with you to clean the river. The other robot says yes. What happens in this case? A certain contract is in place, which alters, in this case, how many apples you effectively get. Some apples are automatically transferred. Robots clean, apples grow. They go into some division of labor, and they sit. There's no path that brings them into a dilemma state. So what happens here? Well, it happens, but there is a transfer of apples, which is here just a normal employment contract you could think of, that they're learning from some set of possible commitments. This doesn't require any altruism. This is at every point, this is the right thing. Like as soon as the one robot committed to give the other one apples for cleaning, it's in the best interest for the cleaning agent to clean, and the other one, yeah, sure. If they don't have anything to do, they will eat apples. So at this point, this is clear. It is also the choice to propose the commitment device, incentive compatible, yeah. Like you're comparing an outcome which is paradise, essentially. There's a working agent who gets something, and there's an agent that eats apples. This is a good outcome. To the dilemma state, which is bad for both. So at every stage, you're purely in the self-interest, and I think there that commitment devices are actually the use of incentive commitment devices is incentive compatible. It is something that's well known. How do you make this formal? This is a Markov game. We have a state space. We have some initial state. This is like the grid world. These things look all a bit more high dimensional. You have vectors of actions, which could here be move up, move down, move left, move right, pick apple, clean garbage from the river. You have a transition function that maps state actions to new states. Here, the state contains apples, location of garbage, and the locations of the robots. And you have a reward function, which in this case gives you number of apples. So we want to bring something new in this. So we bring commitment devices into this Markov game environment. And this we do via a set of potential commitment devices. That's quite similar to the proposal. I forgot the name again of the specification with commitment devices. It wasn't in one of the things, one abbreviation, and a function mapping the set of commitment devices to essentially semantics of the commitment device. The commitment device here is a zero-sum transfer, depending on state. So here it is, if you're in a state where the river is clean, there is a transfer from one of the agents to the other agent. And this is the form of commitment that we're looking at in the example. We also need to blow up slightly this state space by tracking which contracts are currently in force. The rest of this is going to be why this second small idea, I promise the other three will be shorter, is why this works in theory and why this works in practice. Yes.
Can you go back 1 second? Point out explicitly why cannot you incorporate the commitment devices as part of the state space? Why do you need the extra? What is it in the commitment devices that you kind of like code in the formalists in the?
Oh, it is like you can totally view this as this will compile down to another Markov game.
Okay.
And when I tell you how to solve it, you'll see. Okay. First, in theory, we have a theorem for an arbitrary full information Markov game. Full information is here important. I'm going to talk in number 3 about that. Then, for any sufficiently rich contracting space, all equilibria of the augmented game are equal to a jointly optimal policy profile of the original game under the contract proposed in the equilibrium. If that doesn't make sense to you right now, that is fine, because it says only that allowing an agent to contract with sufficiently rich commitment devices mitigates social balance under complete information. Yes.
What does sufficiently rich
high punishments? This is high possible chances. I need to have that. Otherwise, I don't really care. It's going to be degenerate, but there for this theorem, I essentially want to force you, if you're not doing the best thing, I'm just forcing you.
Does it also depend on the dimensionality of theta? If it's a parameterized space and so on, or it's not what rich means here?
No. It's really about the possibility, because it is about, so here it is, really the property that you need is that your contract space is rich enough to detect deviators, well, in some sense. Okay. There, have a look at the paper. I think the theory here is less interesting than actually an implementation. And my goal for you is to get to the point of how would you actually train this? So we can take this game, and this is as you asked, this is just a normal game. You could totally encode that, and you can train it with a generic algorithm. You're just saying there's a first proposal stage, there's some acceptance stage, then you go fair, performs fine. How can it outperform joint? Well, the thing is that if you're doing joint, you really need to look what caused what, because then, like, essentially you're having 2 agents and you're doing something to 2 agents. So you have a 2-dimensional action space, and you need to learn, okay, so if I'm doing this one agent, then this affects welfare in the following global way. If you have a single agent environment that is working under some contract, then they will very easily figure out what their part of the reward, namely their apples, how that depends on their action. This is called in reinforcement learning credit assignment. Which part of your actions do what? It's a much easier problem to decompose. And one of the reasons why you actually would look at independently trained agents, because their problem is much more local. It respects locality, that actions that are taken by a particular agent actually affect their reward quite directly, but not so much the global way. The problem is that this doesn't really scale well to more agents. And one problem is that the contracting space to value for the agents, so to utility for the agents mapping, it's more and more discontinuous over time. Like in some sense, you have having optimal reactions in the sense of best responses, and this gets harder and harder to learn function, and it might not be that there is enough exploration. So what you do to solve this is to say, well, let's decompose the problem. Let's first solve for different possible worlds under different enacted commitments and just learn policies and hence learn values. And after that, just optimize over that. You then have just a function that maps your contract parameters to how much utility is there, and you can optimize as a proposing agent what you do. I see that you're not. No.
Oh, yeah. So like, how does the agent? So is here like the agent is learning what contract to propose
In the second stage,
yes. Yeah.
in the first stage, they're only learning to play under an arbitrary contract.
I see.
Yes. And decomposing these essentially gives you an exploration bonus on this, if you want to view it. But it also essentially brings down the reinforcement learning only to this parameterized problem. This one is then classical search, which is computationally much easier. The key idea, hence, is to learn how to play given a contract before learning to contract.
Yeah, I think partly answers my question, but I was going to say, does this basically end up then being kind of like a stackable game in which you first have to select the contract and then, well, there's some element of kind of subgame perfection here where you like what you're doing is like, for any contract, how am I going to best act optimally, and then you have a contract.
Yeah, here the thing is there is interpolation in that you're really relying somehow on the geometry of your contract space to give you, okay, I only tried 1,000 different ones. Let me use my neural net magic to actually interpolate, okay, fine, play. Yeah, otherwise. But yes. So here in stackable sense, one thing, going back to this, is not a new agent. We're just declaring one of the agents to have the possibility. How you assign that is nothing new. You're not changing the agentic environment. There's still n agents.
One
yes
quick follow-up question, which maybe you're going to answer anyway, but on what kind of time frequency does the contracts like change or get updated?
I will come to this. Yeah. Let's look at more experiments. Princess Dilemma and Public Goods is two classical static games. Harvest is another grid-worldy environment, which is mostly an intertemporal social dilemma, where if you over-harvest now, things won't regrow again. Cleanup is the domain that we have been talking about on the slides. Merge is a self-driving car domain, which is essentially dots on a line chasing each other. So relatively far from realism. And we're comparing the 4 baselines that I told you about already, and this two-step procedure that I proposed in the earlier slide, which is multi-objective contracting, augmentation, learning, MoCA. And what we see is that MoCA scales more nicely. This is kind of what we set out to do, and the experiments confirm it. Future work. Scaling to more agents. Here, one big question is, how can you transfer between agents the knowledge of what it means to contract? If you can do that, then you can just clone things, and you can do it like the Dota 5, where you have 5 times the same agent. So Dota 5 was this OpenAI bot that played Defense of the Ancients. The second one is learned contract functions. So far, I said that there is some given logic to contracts, but you might actually want to have a lower parameterized set of contracts that are more reasonable. And for this, you would need to learn the logic. And there is renegotiation, which is after which time, so you allow for some time, after some time, for contracts to elapse. There's always a trade-off in that contracts run out. the long-term incentives are broken because you know that the commitment is not going to last. So in summary of this paper, social dilemmas arise in multi-agent systems when managing shared resources. Contracting or commitment devices in this environment create incentives for pro-social behavior without assuming any altruism, and letting agents trade voluntarily mitigate social dilemmas in both theory and in practice. So we saw now an example of what's the type? Oh, fantastic! Wow. I started at point now. Anyways, so you now saw the talk at AMAS that my collaborator gave, and 2 comments on here on your stated goal of today with the concrete domains. And I will give them names. The first is Centurion. Here we are working in simulators, and all of reinforcement learning right now happens in higher or lower fidelity simulators. One of the questions that I would give to the crypto community that I see in many of you is, how are you thinking about a simulator versus reality in a crypto environment? Because we have rollouts, so these are simulations of the environment on 100 CPUs in parallel of these worlds. Are you going to simulate a ledger in training? Are you going to simulate a blockchain? Or are you going to simulate smart contracts while you're training? Or is this purely a deployment thing? I think there are several questions around that. And here, how would even reinforcement learning training look with cryptographic techniques, while also realizing that you need to get onto the order of hundreds of millions of environment steps, that this is realistic? Open question. The second one, for an environment like here, is a very particular type of wireheading that I also would like to pose you as an open question. If you're saying that commitment devices are going to intervene directly into rewards that agents get, and I think that there are a lot of arguments for doing that as opposed to intervening into actions or delegation, which I see very often. So I'll say later why. You will run into a situation where you might, as a robot, be able to evade receiving the reward signal from the ledger. If you can do that, that's a perfectly fine way to wirehead yourself, because there needs to be some reward signal that you get instead. If the centralized blockchain tells you, oh, this was actually really not nice of you that you didn't clean, but you, for some reason, can move to a part of the earth where you're actually not able to access the ledger, and there is some decentralized computation which you will need in robotics, what do you do? So here,
They don't know what wireheading is.
okay. So here's you're messing around in your own head. Here it means you can influence the reward signal that you yourself are getting. And here I'm thinking about the application of, if the reward signal depends on some public ledger and you can evade receiving that thing, then that's a very clear reward hack that I see in such an application. And I think that's something to really think about in a real deployment. There was a question.
Yeah, it's, I guess, back on state. Sure. Okay. Yeah. So are the contracts proposed or like enacted unilaterally?
I'm going to come to that in the fifth part. Okay. These are like 2 concrete things that I would love for someone in the crypto space to think more about. The next part is that I would like to be a bit more clear about the thing that I already earlier said with delegation versus transfers. about intervention into games. So if you're augmenting a game to get cooperative outcomes, you can do something like, essentially, hey, I'm not going to do that because I'm actually delegating to another agent. The second thing is, oh yeah, I'm going to just in certain world states, going to transfer. If you're delegating, then what this means is you need to have a fully fledged policy that is run somewhere else. Otherwise, you could influence it, that actually acts for you. If you think about a real robot picking up stuff, you're not going to be able to do that. That any computation on a blockchain will be too slow to get that. You need some local computation. You can send some certificates, but I don't see that. I don't see that happening under reasonable latency. So the whole idea of, and here like a bit more of the blunt person here, the whole idea of, oh, we expect each other's source code, I don't really believe that will be at all working. One thing that can work is to say you have a reference world state. You can call this reference world state the S&P 500. In nowadays, it can be the Fitch rating for Google or for Italy. And based on this, you have certain automatic rules. Flash crash, a lot of things based on these automatic world states. You're saying, I'm going to allow reward transfers based on that. You don't need to know anything about the local computations of a robot. You don't need to know their action spaces. You don't need to have know something about their internal representations. The only thing you need is to know that this thing is optimizing, is maximizing a reward, and you can give it reward. You need some way to make reward comparable across agents. But that's straightforward in many environments. If you're going for an Amazon warehouse, you could say it should be the same reward for every agent to pick up one box. Easy. It's your welfare criterion, but you can do it. So here, delegation solutions, I don't see as not reinforcement learning had. I don't see as scalable. Transfer solutions, I think there is this problem with wireheading. I think it's much more tractable. This brings us to the question of here, contractible outcomes. Number 4. It was actually super crucial for the paper that we have, we don't have incomplete information. We can contract on the true state of the world. This is going to not be true. And in one of the papers from yesterday, or its abstract, was exactly that question. Like, you don't have that the chain knows everything. And in thinking about thinking about how contracting could work in the real world, you really need some sort of the chain meets the real world. So you need some sensors that you can actually rely on. This, I would say, is not necessarily saying that there's a centralization going on. You just need to have some trust if you're leaving the chain. You will need to leave the chain at some point. So one question here is, what is a contractible outcome that you would like to go about to incorporate into your system? These types of measurements, if you're going beyond finance application or transaction applications, are actually not as straightforward. You're thinking about the upper right one, which was the electrical grid. There's a lot of things you might want to contract on that are actually very hard to really control as stable and not hackable. These would be the New York Times headlines. This would be certain things happening even in Mexico, south of the border. If we were talking about Texas, this could be rainfall numbers in Northern America. A lot of things you need to inform these contractible outcomes. If the contractible outcomes are there, you can write good contracts. If they're somewhat limited, you're running into problem called moral hazard that I'm not going to explain to not get over my allotted time. Number 5 is theoretical time. Let me just rewrite this. I think I finished slightly early, by the way. So if you want, I think it's good to have some more conversation. Then, what would you call it? I think we just call this distribution. The part is about the concept of the proposer here. One of the main things why commitment devices are amazing for welfare is that the proposing entity can actually, the proposing entity is aligned with social welfare because they can extract all surplus from doing so. And one thing I want to put into your head in this last thing is, in many applications, that's not a bad thing. This is the beauty of working with robots. If you're in an Amazon warehouse and you're making one robot extremely poor, you don't fucking care. It's not really a problem because robots don't starve. There's a question of like, there's ownership of robots, but you don't necessarily really care. In these environments, having one agent who can give it a lot of a lot of human society names that sound bad, but you don't need to. You can have one robot who extracts all the surplus from the system, and the system behaves amazing. All the problems of commitment races or other miscoordination problems arise from this assumption that you need to allow every agent in your system to get the fruits from that. And I want to give to you, if you're really going and engineering a multi-agent system, just don't allow that. Just declare one agent who is going to be really rich and run with it. In many environments, that's actually going to work. The only problem is the miscoordination from this desire of humans to create something fair, which in robot situations is not clear. It's not that the robot is entitled to getting a certain amount of reward. And you also get into more that's miscoordination also leads to then arms races and ineffective investments in that. Just saying there's solutions out of that. If you just drop your fairness consideration between robots, which I think is fine if you're thinking about it. So going through the 5 ones again, I first given 3 examples of mediators, declare leaders, and subgame-perfection as broad solutions to the coordination problem. Then I give you one concrete situation of the declared leader and talked about how you would do that in grid worlds. I also gave you 2 concrete problems that I think are important to work on. I argued that transfer-based commitment devices are the way forward as opposed to delegation-based ones. We will need some contractible outcomes where the chain meets the real world, and thinking about which these should be is an important question. And I argued that caring about distribution is often a problem that could be a problem that makes it much, much harder to actually make progress, which you might not care about in AI. Looking forward to all of your thoughts.
So, great talk, by the way.
Thank you.
So I have one question on an interesting way to see, I guess, what we just said.
Yeah.
Which is, So something that some people are thinking about is proposer commitments in a blockchain context, right? And I think that highlighted some of the ways, or basically highlighted the concept of contracts that the validators in a blockchain can enter into. And something interesting about that is that the contracts that are actually enforceable are, the contracts that enforceable by the chain are the contracts that the chain has information about. But something that we saw was like two ways in which the blockchain can learn, which is the first one is obviously through consensus. So learning whether, for example, say a contract was, the commitment was properly executed in the real world, or something in the real world happened. And the other way of learning about the real world from inside the chain is through cryptography. So, for example, posting a cryptographic proof, something, and then verifying the proof as part of the protocol, so to speak.
Yeah.
And the other thing I wanted to ask you about is,
so what I could quickly comment on that, because one thing that here also, just as like outsiders look, or now economists has look on things that I read in preparation for this, there seems to be an interesting bias in crypto talking about what the chain does. That's very financial economics, I would say. It's all about information aggregation. It's like, if all information is aggregated on the chain, that's good. And here, it's not necessarily that you really need for a well-performing system to know all these things. The thing that's really important is, okay, what in the real world happens? Are there flash crashes and so on? I totally understand it if there's this more narrow view of the chain as being a transaction medium, then it's all about that. But you can have contracts with severely limited information. There is going to be strategizing with that, but that's not bad, and that's not bad. Like many people are saying, oh, we need to make it strategy proof to essentially make it robust against strategizing. That's not my view. It's gorgeous. A lot of good outcomes are coming out of strategy. So,
I totally agree, by the way. And in fact, people argue that those systems have a bit of an optimistic flavor, where, for example, there's some, there's asymmetry or information that will arise in the future, then some commitment or some trust is put on today, and when that information becomes available, then the agent that made this assertion, so to speak, about the real world can be punished as a way of enforcing the fact that
listen. Yeah. And here also, like, these are all relational contracts. Like one very, very standard way to do these types of punishments, we call relational contracts, which is just like, I'm struggling to work with you, like if you lie to me. So just here, but the totally like natural way of humans to enforce things, or you're ending friendships.
Yeah.
Okay.
Yeah. And then what about, for example, contracts where the enforcement? So you were saying, there are contracts that due to incentive compatibility, they have to be enforced by say some external thing to the parties involved in the contract. But what about contracts that lie in between, where they can be, for example, mildly influenced? The enforcement of the contract can be mildly influenced or somewhat influenced by the parties that take part in the contract. So in other words, they lie somewhere in between the absolute enforcement, depending on the external world, but they can be influenced by the agents. And if you think there are some interesting ways in which that could be quantified, say, for example, these contracts are robust. Say,
here, read this paper. That should be Hart, the Oliver Hart, the Nobel laureate in the Harvard Business Review. Should be 2019.
There is this thing that there is this very funny thing that companies that are cooperating with each other are writing down values formally. They're written down things, but they're clearly not non-enforceable. This paper makes the claim that there is a coordination aspect to partly formalized, but actually punished in the real world by actual humans things. And one thing I'm kind of thinking here is that I'm also implying, I think here, that you can influence how something that's semi-automatically enforced, that won't be that tractable. I do, the thing that I'm saying though is that having written things that govern or that outline how punishment is going to happen in the more subgame-perfect world, that we have these with humans, and these are potentially totally feasible for a ledger, that you're essentially saying, here are recommendations to punish for people. We're not forcing you to do it. You do it in the real world, but let's write this down. And this I have consensus. But there, I think we will probably have much better ideas. Just read this very general audience. You were first, then you, then.
Yeah. So just one comprehensive question.
Yes.
In the paper that you talked about, your paper, is it just the one distinguished? The only one who can propose contract?
We give general enough. Like you could have an arbitrary agent, and you can transition back into contracting nodes. As soon as you have several contracting agents, you lose the theoretical guarantee, because I'm going to try to influence the world state to make you propose in the future state a contract that's better. And you totally see that. Like if you have, for example, re-elections in associations, that people will try to influence future elections already. Arguably, the United States is one such association. Then you.
Question about the kind of partial observability thing. So obviously that breaks a bunch of things. Yeah, I wonder if there's a way. Do you have any thoughts on the feasibility of kind of like it failing gracefully? So the more uncertainty you have, then the kind of like the more kind of bets are off, so to speak. Or is there just like pretty kind of discontinuous thing being like, cool, if it's not fully observable, then you can just get kind of like arbitrarily.
Yeah, there is. This might be cool. This is like very econ maths, but one lesser known saying. So the underlying thing of incomplete information is the theorem of Myerson in that instead of that's So I'm taking your question as, is this continuous or is this discontinuous? Yeah. If we're getting imperfect, I'm claiming that this is continuous.
Continuous
in the distribution. So continuous in the distribution of incomplete information. Yeah. So here in Myerson, Setter's way, you have two agents, the buyer and a seller. They have this good. Let's make it an iPhone. Both have some types. There's some uncertainty over that. Any mechanism tries to elicit this information. The claim is that there is no efficient. That means whenever there would be gains from trade, the trade actually happens. Mechanism for this. The reason is that the fact that you would be willing to trade at a certain price tells me something which I want to extract something from. This is like the whole thing about information rents here. The thing here is that if you're moving to the vicinity in some metric on probability distributions of a concentrated thing, so where you don't have limited information, that actually, it probably would need to be something like Earth mover distance. It's actually going to be continuous. because you can only lie so much. It's like an arbitrarily small gain that you're making, which is going to reject only arbitrarily few trades, which makes it continuous. So here, I would take this one as it's not that problem. The main thing with like the really bad outcomes with unraveling in the market for lemons, after loss. The thing is, this is very, very strongly non-observable. Like you don't observe a ton of things about cars in that. So here, yeah, almost making this not reading list. Lemons. Yeah, here lemons meaning cars, not meaning fruit. You awesome.
Yeah. Thank you for Dr. Andreas' work. So you said that the high-level implementation, but I won't pass on the old theory. That so when you describe the main pyramid, there is enough space of
Yep.
You said that you need some kind of punishment, right? Something to be able to enforce the outcome. And I think the analogy of in the blockchain space is exciting that is implementing the Ethereum blockchain. And there is a question.
Sorry, say again. What is implementing? What is implementing what on the chain?
Slashing. So if some people do something wrong, they lose a lot of money. They lose all their money.
Okay.
And so that's called slashing.
Yep.
So at the deposit that your current place to be around them. They perform some duty. And there's a question, can we show that some things are impossible if you don't have these very, very strict punishments? And I think that's also central in your work, that if we don't have this rich space, or if we don't have these very strict punishments, we cannot show something. Do you think that are there interesting results without these punishments, or that we can have
everything is possible without punishments.
You think everything is also possible. So, but why do you need the rich space so you don't have?
Oh, the proof is easier. The proof is easier.
There's so you can do that also without it.
So here, like the thing there is, what you exactly need is dependent on your game. It's just like, it's a very simple thing to just say, I'm going to burn down the earth if you're disagreeing. Easy. But really what you need is, what is your best deviation? Let me just charge you to disincentivize you to take that best deviation.
All right.
If this is exactly what you need. And often the best deviation is not that profitable.
Right.
So you need something very small, and often even the value of deviations will is some smooth function. If the function is a smooth function, also underlying parameter. So you don't need crazy things. And there's no impossibility in that. One thing here that I didn't bring up, we're definitely in the button now. This is now Ben Chom's term. This is moral hazard and observability. Here it is. There's some hidden action that is taken. There's some outcome that's observed. You don't know exactly how bad it is. You have some smooth, actually, incentive contract that is enforcing it, and it's mostly depending on risk preferences, which I think then, as a governance group for an Ethereum blockchain, I think actually thinking about risk preferences of people on the chain would be relevant to see like how much do you need. In our work, everyone is risk neutral, so you need extremely strong punishments.
The question about this delegation risk transfers thing.
Yes.
Which actually might be somewhat related to Casper stuff. Yeah, I think you make some good points in favor of transfers. But I wonder about the limits. Like, essentially, if you can delegate to an arbitrary agent, like, let's say you could, like, delegate, rather than delegating their, like, giving a specific algorithm, you can just delegate a reward function and have them optimize this, right? This reward function. Then you have a lot more freedom than if you can only commit to transfers, right? Because if you can only commit to transfers, like, utility has to be conserved, or maybe you're allowed to burn money, but, like, that's obviously somewhat unfavorable. Whereas if you can delegate arbitrary utility, then you can
yeah, I mean, you just have a lot more freedom, which will be useful.
I would push back by saying, but I think it's kind of a science fiction type of critique, like how that there is a more direct world here. So who is delegating? Clearly, we are already delegating to machines. We're delegating to machines in Amazon warehouses. What you seem to be saying with delegation here is that we have robots delegating to other robots. One of the questions with, or one of the beauties of reinforcement learning policies is that they're digital goods. You can just copy them. So if you would like something that optimizes in an amazing way, just deploy it directly. No delegation is needed to do that. If you are saying that the delegation actually gives me more flexibility to implement stuff, well, the theorem that I showed you is telling us that the decently full information case, no, it doesn't give you more. Because in some way you can view transfers as like large relaxations of limits on what you can do. Like I'm just disincentivizing you in some smooth way from doing something. But there's like, I claim is actually not more powerful. Even if it were more powerful, in a world where we have algorithms delegated to other algorithms, I think we first have the step that actually algorithms just use certain technologies independently. Like one of the beauties, I think, of this paper is it essentially is a black box intervention. You're just switching this on. It's only going to improve the performance. You don't need to tune anything about that. If they can contract, they will get better social outcomes with this distributional concept. They will get better social outcomes. Is that I think the main point here is, and that's maybe something for offline, is that I am claiming that you are not going to be more performant for social welfare with that. So the flexibility actually doesn't buy it.
Yeah, I'd like to discuss this.
Yeah. Let's do that offline.
Coming back to, I thought it was really interesting that you had this kind of two-step part of the mocap where we have like kind of basically more explanation of exploration kind of put into the like I was wondering if that two-step kind of structure of kind of hierarchical in sense is needed to achieve this better outcome, or if you just kind of added them at an epsilon really parameter to the searching across contracts will work.
This is a question for are you interested in that as a pure reinforcement learning question? Are you interested in that in a system engineer?
I'm interested in both, I think, but like I'm kind of interested in what's the role of the hierarchical part and two-step like kind of structure of the model in achieving those better results, or is it just like kind of a way to augment the exploration parameter?
There is the short answer is you could build systems where you have separate exploration rates, and this is going to perform worse, actually, because the learn in early phases where everyone is kind of stupid, you even trying to learn to contract doesn't make sense. You need to have a head start on how you have it. That's actually really performing better to say, let's first offline learn to behave reasonably as agents and then do it. It will work. Like we didn't run this, but I expect that it will work reasonably well. It will be joint, but it won't be this.
I think you also mentioned something regarding agency concerns. Can you elaborate on that?
Yeah, I might only have put that in the abstract. So when I was talking about this wireheading example, there's all this underlying question around if you are deploying this, there needs to be some ledger or some public computation engine that gives these rewards to you. And the problem with that is that leads to happen very, very quickly. Like if you are in a, let's take warehousing as an example, like there is all super centralized right now. If you want to give a good reward signal for an agent, which is well shaped, you need to, at least when every package, when any box in the whole warehouse is picked up, you need to send something to all robots, and they will need to receive it. So this puts you into an environment that at least the computation that you're having with sending is on the order of half a second, which you can totally do. Depending on which environments and how distributed we are, this is going to be a concern. And for me, the more crucial one, which I then also wrote down, is this wireheading, that the agents have an incentive to make it harder to receive the rewards. But they're like, honestly, I don't even know how fast computation on the RAM is right now. I was
500 milliseconds is realistic. Yeah.
Okay. So it's half a second. Good. So then we are exactly in this use case, realistic, that this could happen on the ledge. But there, essentially the question is like, Ed, in what time frame would you like to give agents something about their, some information about their externality for them to take good actions? And if it is not too fast, that is.
I think we have 5 minutes until Casper.
Cool. Write me an email if there's more things that you would like to discuss. And thanks for having me.
Yeah, thanks for coming.